Hello everyone, welcome to this video. In this video, we shall be solving this question which states that if G be a finite group with more than one elements, right? So we are given that G is some group having order as finite. So it contains finite number of elements within it, correct? So we assume that the finite number of elements it contain is finite, correct? It could be any number. Now we have to show that G has an element which is having prime order, correct? So it definitely has an element which has prime order. So we need to prove this thing. So what we do, we prove it by the method of contradiction. So we first of all assume that G does not has an element of prime order, correct? So if it does not has an element of prime order, so definitely it would have an element which is having a composite order, correct? So we assume that element to be A. So A be such element belonging to G such that order of A is M and M is a composite number, correct? So therefore you can write M as product of various prime numbers or the powers of prime. So we assume that P1, P2 up to Pk, they are the prime numbers and we can raise them to power n1, n2 up to nk, which are integers. So you can write M, this composite number, in this form. That is the very basic result that we have used here. Now because we have assumed that the order of A is M, so this A raised to power M is equal to E. We can write it like this. Correct. Now what is this M? Your M is given to be this P1 raised to power N1, P2 raised to power N2 up to so on Pk raised to power Nk. So in place of this M, you can now write P1 raised to power N1, P2 raised to power N2 and so on up to Pk raised to power Nk. Correct. Now what you can do to this power, you can subtract -1 and you can add -1. You can do that. There is no issue because they are nothing but 0. So that is quite obvious. So this is what we have done over here. Now you can split up the powers. You know, A raised to power B into A raised to power C. This is A raised to power B plus C. So now we have this result. We can split it up into these kind. So you can put n-1 in one brackets and 1 in one bracket. So you can write it like this: P1 raised to power n-1 into P1 raised to power 1, correct? Now what you have A raised to power B into C, correct? So you can write it like this: A raised to power B into raised to power C. Why? Because the laws of exponent says you can just multiply these two powers here and you get the result like this. So now we have so many terms here in multiplication. So what we can do, we can take out this term outside the bracket so that we could have A raised to power P1 n1 minus 1, P2 n2, Pk nk, correct? And whole raised to power P1. Why? Because when you open up this power, it would be multiplied to all of these terms, and all the terms, because they are in multiplication, so this could be commuted with each other, correct? So therefore now you have written some element here as the power of P1, where what is P1? P1 is a prime number and it give you equal to E. So therefore in this case the order of this element becomes equal to P1, where what is P1? P1 is a prime number. Thus we found some number A in the group G such that when we raise it to the power P1 raised to power n-1, P2 raised to power n-2 up to Pk raised to power nk, right, we get identity. So that means this element here has prime order, and moreover this element is present in G. Why? Because A was assumed to be present in G, and when we raise it to some power, it would also be present in G by the closure property of group, because G is given to be a group. Therefore this member is a member of G which has prime order, and this is what we wanted to prove here for this particular question, correct? So we have proved that if G is some finite group with more than one element within it, then it has an element of prime order within it. So I hope you understood this question well. Well, that is it for this video. Thank you for watching.